This is Lecture 1 for Module 1, which is one-dimensional motion in the book Problem Solving Guide for Mechanics and Thermodynamics. First of all, you might think that you'll be able to solve physics problems after watching this video. This is not the case. Watching a video explaining the concepts will not give you the ability to solve challenging physics problems involving these concepts. It's like watching a video on how to play the violin and then expecting to be able to play the violin. Or watching a video on juggling and expecting to be able to juggle just from watching the video. Just like any other skill, the only way to develop mastery is to practice. The way to develop the skill to solve challenging physics problems is to try to solve challenging physics problems. This video is going to give you some pointers, some advice, some familiarity with the equations, but you have to put in the work. It's just like the swim coach telling you, don't take your head out of the water, rotate your hips more, kick harder. You can get all the advice you want, but you have to put in the work. You have to get in the pool. To develop your skills optimally, you're going to probably watch the video with a piece of paper and a pencil, pause the video, think for yourself. Really try to understand what's going on. Your mind has to be on when you're watching the video. Your development comes from practicing, not from watching the video. You have to put in the work. So if a student is not passionate about learning physics, there's nothing you can do to force him or her to learn physics. You can't drag them kicking and screaming to learn physics. On the other hand, if a student is passionate about learning physics, there's nothing you can do to stop him or her from learning physics. Okay, here's our sample problem. This is what you should be able to do eventually, not after watching the lecture, but after thinking hard. It's a problem from the book, problem 136. Two cars are driving. The blue car is going 90 miles an hour. The red car is going 60 miles an hour. The blue car is passing up the red car. When they're exactly even, they both notice that the bridge is out 250 feet ahead. They both slam on the brakes. At the same time, they slow down at the same rate. The red car stops at the end of the bridge. The blue car, of course, does not stop at the end of the bridge. It goes over. The question is, with what speed does the blue car go over? How fast is the red car going when the blue car goes over? And where is the red car when the blue car goes over? So solving physics problems is a lot more thinking than doing. You're going to be doing a lot of thinking. You have to do this take inventory phase in the beginning where you're trying to figure out what the heck's going on here. You're not going to know how to do it right away. You have to think. This is good news because it's going to develop your general problem-solving ability that you can apply not only in other subjects but in everyday life. Your ability to think and figure things out for yourself. So, the subject of this module is one-dimensional motion. That's motion along a straight line. So we're only going to do straight up, straight across. So a car driving along a flat road, straight flat road, a ball thrown straight up. That's one-dimensional motion, back and forth. We're going to be using the concepts of distance, speed, acceleration, and time to describe the motion. How fast is it going? When is it doing it? How fast is the speed changing? And where is it? So let's do horizontal motion at constant speed in a straight line. Start simple. A car travels at a constant speed of 60 miles an hour for 5 hours. How far does it go? Your first thought should not be, what equation do I use? We have to disabuse you of that strategy if you have it. Equations can be used as an excuse to avoid thinking. I don't want to think, I just want to plug something into an equation. There's nothing wrong with using an equation in general, but you should understand what the equation's doing. What's going on here? What does this mean? Does it make sense? The average speed is the distance divided by the time. You probably knew that before you came into this class. Average speed, distance, total, time taken. The answer is 300 miles. If you go 60 miles an hour, 60 miles each hour for 5 hours, you're going to go 300 miles. You don't need an equation for that. If a sprinter completes 400 meters in 50 seconds, 400 meters over 50 seconds, his average speed is 8 meters every second. You can use the equation if you want. In the special case, it's a special case in which the speed is changing linearly from the initial speed to a final speed over some time interval. The average speed is the middle speed. It's the average of the initial speed and the final speed if it's changing smoothly and continuously and linearly. So a motorcycle's going 30 meters per second, slows down linearly to a speed of 20 meters per second in a time interval of 5 seconds. What's the average speed of the motorcycle over the 5 seconds? If it goes from 30 to 20 linearly, the average speed is in the middle. It's 25 meters per second. Add them up, divide by 2, that's the formula for the average. But that's true only if the speed is changing linearly. The average speed is 25 meters per second. A good example in which the average speed is not the middle speed is the sprinter. Well, the sprinter starts at rest, the gun goes off, it goes 400 meters in 50 seconds. The final speed is something like 8 meters per second. Depends if speeding up, slowing down, getting tired, something like that. But the average speed's not 4 meters per second. Starts at 0, ends up at 8. The average is not 4 because the speed's not changing smoothly. It changes very quickly in the beginning and then levels off. Now let's get the distance traveled by the motorcycle over the 5-second transition. The motorcycle goes from 30 meters per second to 20 meters per second over a time interval of 5 seconds. We know the average speed. It averages 25 meters every second for 5 seconds. It's going to go 125 meters. That should make sense to you. So now let's think about acceleration. The concept of acceleration. Linear acceleration is the rate of change of the speed. How quickly is the speed changing? So let's consider this problem. A car goes from 0 to 60 in 12 seconds. Speed is changing at a constant rate. What is the acceleration? What does that mean? What is the rate of change of the speed? How quickly is the speed changing? Don't think, what equation do I use? Wondering which equation to use is not going to develop your problem-solving ability. Just think, describe it. 0 to 60 miles an hour in 12 seconds. And you have to put units in so people know what the heck you're talking about. What's going on with the speedometer? Whether it's analog or digital, think about that. How quickly is the speed changing? So pause the video and think about it until you say, this has to be right. It makes perfect sense. I understand what this means. The answer is 5 miles per hour every second. That's the acceleration. Starts at rest. After 1 second, it's going 5 miles an hour, 2 seconds, 10 miles an hour, 3 seconds, 50 miles an hour, 4 seconds, 20 miles an hour. If it keeps going up by 5 miles per hour every second, after 12 seconds, it's going to get to 60. The acceleration is 5 miles per hour per second. Rate of change of the speed. Some teachers don't like that mixed unit, but I love it. It's great. If you're used to the English system of units, that's what the acceleration means. How quickly is the speed changing? It's the most intuitive for me. Now let's go back to that slowing motorcyclist. She went from 30 meters per second to 20 meters per second over 5 seconds at a constant rate. How quickly is her speed changing? What's her acceleration? Think about that. Does it make sense to you? You have the answer? Minus 2 meters per second every second. Now, another way to write it is minus 2 meters per second, or minus 2 meters per second squared. It's not very intuitive what a square second is, but it's minus 2 meters per second every second. There's 2 second units in the denominator. Now let's do the vertical direction. Vertical direction involves gravity. When an object is in free fall near the surface of the Earth, you drop something, it accelerates at 22 miles per hour every second. Every second the speed changes by 22 miles an hour, ignoring air drag. So at 0 to 60 under 3 seconds. A Tesla Plaid can do that on a level road. Incidentally, so in SI units, the acceleration due to gravity on the surface of the Earth is about 9.1 meters per second. every second. And unfortunately, we'd love to use 10, and we're just going to do that because we like 10. We're going to use lowercase g for gravity, and we're going to call it 10 meters per second every second. It's about 32 feet per second every second, and about 22 miles per hour every second. The goal of the class is to develop problem-solving skills and not to determine where a baseball or an arrow or a cannonball is going to land with any precision. If you're going to do that, you have to include air drag and a whole bunch of other stuff. So our answers aren't going to be exact, but if we ignore air drag, they're going to be wrong anyway. So let's just use 10 for G. We're going to avoid the use of a calculator in many cases. And we'll be able to just think, and that's what we want. We want to think. So we drop an object from rest. What's going on? Here's the speed. Here's the time. After 1 second, it's going 10 meters per second. After 2 seconds, it's going 20 meters per second. After 3 seconds, it's going 30 meters per second. After 3.278 meters per second, it's going 32. After 3.278 seconds, it's going 32.78 meters per second. Acceleration is 10 meters per second every second. Now, sometimes you throw things up. We have to think about that. If you throw something up, now we're going to talk about the velocity because we have the direction in there. If you throw something up at 30 meters per second, at 0 time, it's going 30 meters per second. What's going to happen when you throw it straight up? Well, it's going to slow down. How much does it slow down? It slows down 10 meters per second every second. That's what gravity does. After 1 second, it's going 20. After 3 seconds, it's going 10. After 2 seconds, it's going 10. After 3 seconds, it stopped. It took gravity 3 seconds to take away 30 meters per second because it takes away 10 meters per second every second. This is the peak. This point here represents the peak. The speed is 0. It stopped. A second later, it's coming down. The velocity is minus 10, then it's minus 20, then it's minus 30, etc. So let's do a problem involving gravity. A sandbag is dropped from a hot air balloon. How far does it fall in 4 seconds? Well, it's dropped from rest. What does gravity do? It changes its speed by 10 meters per second every second. After 4 seconds, how fast is it going? Do you have it? 40 meters per second. Since it's dropped from rest, the speed is changing linearly by 10 meters per second every second. Starts at 0. The average speed over the 4 seconds it's falling is 20 meters per second. If it averages 20 meters every second for 4 seconds, it travels, pause if you don't have the answer, 80 meters. That's the answer to the problem. If we use 9.8 meters per second squared for the acceleration due to gravity, we're going to have to use some equation, and we're going to calculator, and we're going to get 78.4 meters, and the difference between 78.4 and 80 is not that much. And we're ignoring air drag anyway. So let's just rely on thinking. We don't want to be plugging numbers into equations. Thinking, reasoning, problem-solving skills. That's what we're trying to do. Equations are fine if you fundamentally understand them. I use equations all the time. So what's the equation for one-dimensional acceleration? Let's derive that. Let's think about it. What does it mean? Acceleration is how the speed is changing in one dimension. So it's delta v divided by delta t. So v final minus v initial, and we don't say t final minus t initial. We know it. We know what this t is. This t is the time it takes to go from v initial to v final. That's the time interval between those two v's. And that's constant acceleration. This should make sense to you. Change in speed over time. So we can use this equation to get the acceleration of the car that went from 0 to 60 in 12 seconds. We know what it is. Delta v divided by the time interval. 60 divided by 12 is 5. The units are miles per hour per second. Now let's get the acceleration of the motorcycle. Motorcycle went from 30 to 20 meters per second in 5 seconds. Should make sense to you. 20 minus 30 is minus 10. Minus 10 divided by 5 is 2 meters per second each second. There's more equations of kinematics, but they're not fundamental. We're just going to combine the two equations that we already know. So here are our definitions. These make sense to you, should make sense to you fundamentally. And we have the average, it's just v initial plus v final divided by 2 if the acceleration is linear, and we have to remember that we're making that assumption for these equations. If we combine the last two equations, these two right here, we can write this. That's v average. It's just add them up, divide by 2. The equation for the acceleration can be written like this. V final equals where you started, how much did you change, what's the rate of change, and how long did you do it. Should make sense to you. We just rearranged the equation for acceleration, put the t on the other side, add the v initial to both sides, and we get this. So we can substitute this expression for v final into the equation for x right there. We get that, and we can multiply all this out. We have a v final, a v initial, that's 2v initial divided by 2 times t, and we have 1/2 at times t. That's what it looks like. We derive this equation from the two definitions. This equation doesn't have v final in it. Similarly, we can solve this equation for time. Divide both sides by v initial plus v final divided by 2. We can substitute into this equation, and we get this. And then we're going to do a bunch of algebra and rearrange this. We have difference of two squares eventually, and we get that. That's not so intuitive, but it's convenient because it doesn't have a time in it. If you don't have a time, you can use that equation. If you use this equation to get an answer, you should really confirm the result with some more intuitive. Make sure it makes sense. So the equations that we use to derive these extra two equations assume the acceleration is constant. If the acceleration changes over the time t, these equations are no good. This assumes that the acceleration is linear. The transition from v initial to v final is a linear transition. Otherwise, these are no good. So let's use these two equations and practice using these two new equations to confirm what we already know. So the motorcycle went from 30 meters per second to 20 meters per second over 5 seconds. We used her average speed to get that she must have traveled 125 meters. Let's get the distance with a different equation. How about this one? Distance is 1/2 at squared plus vit. We know all those numbers. The acceleration is minus 2 meters per second every second. The time is 5 seconds. The initial speed is 30. So multiplying all this out, the 2's cancel. We get 25. That's negative. And this is plus 150. We get 125 meters, which is what we got before with the average speed. Now let's use this equation to get the same answer. Okay, there's v final is 20. V initial is 30. Acceleration is minus 2. Let's solve for x. When we square 20, we get 400. We square 30, we get 900. We subtract 900 from both sides, we get minus 500. We divide both sides by 4 meters per second every second. All those units cancel out except for 1 meter units in the top. Minus 500 divided by minus 4 is 125 meters. Of course, all correct paths lead to the same solution. Now let's go back to that sandbag that was dropped from the hot air balloon, dropped for 4 seconds. We used the average speed to determine it fell 80 meters over the 4 seconds. So let's get the distance with a different equation. 1/2 at squared plus vit. The acceleration is minus 10 meters per second every second. The acceleration due to gravity. Before we do that, we should use y because we're doing the vertical, up and down. Let's just get used to that. Acceleration is minus 10. Time is 4 seconds. 1/2 minus 10, 4 squared, 16. That's 160 divided by 2 is 80. Initial speed is 0. So we're done. Let's drop from rest. So we do the calculation, we get minus 80. It went down 80 meters. When you drop a sandbag out of a hot air balloon, you shouldn't need the negative sign to tell you it's going down, right? We know it's not going up when you drop something. Just as before. Now, we use this equation. We got y's in there now. Vertical direction. Initial speed is 0. 40 squared, 1600. The acceleration is minus 10 meters per second every second. 1600 divided by 20 is 80, and the unit is meters. Fell 80 meters. get the same answer if we do it right. We should not be surprised because those two new equations came from the definition that we used to get the answer in the first place. So the 4 equations in kinematics are these. These assume that the acceleration is constant. This is true all the time. So now you have the equations. These equations are the knowledge you need to solve one-dimensional motion problems. This is not enough. Knowing the equations is virtually useless if you don't have problem-solving skills. If you want to become a great sculptor, you need a lot more than a hammer, a chisel, and a block of marble. You need skill. You don't need the tools. Here's the tools right here. These are the tools. You need some skill in using these tools. Knowing the equations of motion is as useful to solving physics problems as knowing the steps of juggling to be able to juggle. So here are the steps for juggling. Find 3 balls, hold 2 balls in one hand, 1 ball in the other, elbows bent 90 degrees, palms face up, toss one of the paired up balls in the air gently, toss the ball in your other hand into the air, toss the last ball that's in your left hand. I'm pretty good at the first 6 steps. It's 7 and 8 that mess me up every time. Catch the balls in the order that you threw them. Repeat. Well, you can study these steps for juggling. You can memorize these steps you can know how to juggle mentally. You know the steps. But the only way to become a good juggler is to practice juggling. Solving physics problems is no different. It's a skill you have to practice. Students say, I understand the material. I can follow your lecture. When I watch the videos, I say I'm nodding my head, but I have trouble following the problems on the exams. Of course you can't. You can't learn to juggle by watching other people juggle. Problem-solving skills are universally applicable. That's what we're going to be doing in this course. So here's some rules for becoming a good problem solver. These aren't rules for getting the answer. These are rules developing into a good problem solver. Think about what's going on. Take inventory. Draw a diagram. Think about the diagram. Does this make sense? What's going on here? What's the answer going to be about? Think about how to attack the problem. What strategy do I use? If you can't find a strategy, go backwards and do not go forwards. Go backwards until you get to something like distance is average speed times time or something. I understand that. Let me do that. Then execute your attack. Think about your answer. Does it make sense? If not, go back. Think about the answer. Think about what's going on. There's no rule here that says thumb through the book looking for an equation to use. This is not a good strategy. You have to think. So, here's problem 136. This video was not designed to train you how to solve this problem. The purpose of the video is to let you know it's okay if you don't know how to solve the problem. Most of the problems you look at in physics, you say, I got nothing. I don't know what to do here. I have to think every time. Taking a good inventory, think about what's going on. You got to start trying stuff and see what works. That's how you develop skills. You try stuff and you see what works and you understand what works and then you understand what doesn't work. You develop your problem-solving intuition. You develop your skill. The best jugglers are the ones that drop the ball the most time. When you see somebody that's a really good juggler, say, man, that person must have dropped those balls so many times. That's how you get better at physics. You do it wrong many, many, many times. And then you eventually learn how to get to the answer efficiently. That's lecture 1.